thank you so much for joining me for this video. Today we're going to be looking at ozone depletion. So ozone is formed naturally in the upper atmosphere and is beneficial because it absorbs UV radiation. Chlorine atoms are formed in the upper atmosphere when UV radiation causes carbon-chlorine bonds in chlorofluorocarbons to break. And chlorine atoms catalyze the decomposition of ozone and contribute to the hole in the ozone layer. We're going to appreciate that results of research by different groups in the scientific community provided evidence for legislation to ban the use of CFCs as solvents and refrigerants, and chemists have now developed alternative chlorine-free, and by the end we should be able to use equations such as the following to explain how chlorine atoms catalyze decomposition of ozone. Now we're going to look at haloalkanes and the environment. So chlorofluorocarbons are haloalkanes containing both chlorine and fluorine but no hydrogen atoms, such as CCl3F. And these are normally unreactive under normal conditions. Shorter CFCs are used in aerosols, propellants, and also fridges as they are gases. And longer CFCs are used in dry cleaning and degreasing solvents as they are liquids. And it's quite important to remember some of these examples of what we use CFCs for. CFCs eventually end up in the upper atmosphere and they decompose in UV light to give chlorine atoms, which are chlorine-free radicals. And these chlorine-free radicals decompose the ozone layer, causing a hole. And we need the ozone layer because it absorbs harmful UV radiation, which can cause skin cancer. So here we have the two equations that occur. So in the first reaction, we have a chlorine-free radical reacting with the ozone, so O3, and this forms a ClO free radical and oxygen. And then this ClO free radical then reacts with some more ozone, and this forms two oxygens and a chlorine free radical. We can describe the chlorine free radical as a catalyst, as it's always regenerated at the end. So overall, the reaction is that we decompose two molecules of ozone, so O3, and we form three oxygen molecules. Now, the really important thing to know is that the chlorine-free radical is not destroyed in the reaction, and so it reacts with more and more of this ozone, and so depletes the ozone layer. So it gets thinner and thinner. And because of this, CFCs have now been phased out and replaced by other safer compounds that don't deplete the ozone layer, and they're called hydrochlorofluorocarbons, and so they have chlorine and fluorine and also hydrogen. However, because we've used loads and loads of CFCs in the past, we now have a lot of it still remaining in the atmosphere, and so it'll take many years for the ozone layer to recover. And it's also really important to remember these three equations, so the two-step equation and also the overall equation for the decomposition of the ozone layer, because it's very commonly asked in exam questions. So now we're going to look at some questions. For question 1, tetrachloromethane is an effective fire extinguisher, but it is no longer used because of its toxicity and its role in the depletion of the ozone layer. In the upper atmosphere, a bond in tetrachloromethane breaks and reactive species are formed. For A, identify the condition that causes a bond in tetrachloromethane to break in the upper atmosphere. Deduce an equation for the formation of the reactive species. So this question is basically about chlorofluorocarbons and how they can deplete the ozone layer. And so what we're looking for is a chlorine-free radical. So the thing that causes a bond in CCl4 to break would be UV light, because that's what we need for an initiation step of a free radical substitution. So UV light is the answer. And then deduce an equation. So we start off with this CCl4, and then using UV light, we can then form CCl3 dot, so that's a free radical, and also a chlorine free radical, that's CCl3, sorry. And this is the equation. And then for B, one of the reactive species formed from CCl4 acts as a catalyst in the decomposition of ozone. Write two equations to show how the species acts as a catalyst. So these are the two equations that you must know for the exam because it comes up so often. So you start off with a chlorine free radical and it reacts with some of this ozone, O3. And this forms a ClO free radical and also an oxygen. And now the second step is that this ClO free radical then reacts with more of this ozone to form 2 oxygens and a chlorine free radical. And then this chlorine free radical then repeats the process and so starts a chain reaction.